Now that we've established the basic concept of a phase and a fluid, let's start estimating the flow rate of specific components through our system. Let's imagine that we have some fluid that's flowing in a pipeline, and that in that fluid we have a specific component, component A. So these little dots represent component A, and we are interested in estimating the number of moles of A that pass across a specific point in the tube. So let's call this point Z. So there's a specific location down the tube which we call Z, and let's say we are interested in a specific time interval delta t. So perhaps delta t is something like 10 minutes or something like that. So we would like to know how many moles of A transfer across this point over time period delta t. So we are going to call that quantity delta NA, and we can acknowledge that the number of moles of A that pass through here over delta T, that must depend on the concentration of component A in this fluid. So we can define the concentration Ca. So the number of moles of A that transfer in that time is going to depend on Ca, and then it will also depend on the volumetric flow rate Q. So Q is the volumetric flow rate, so volumetric flow rate times the concentration. This is going to give us the moles per second. This is going to give us the molar flow rate. So the molar flow rate multiplied by the time change, that tells us the number of moles that left the space. And this volumetric flow rate we can rewrite in terms of the linear velocity. So simply the volumetric flow rate is going to be the linear velocity multiplied with the cross-sectional area, which we will simply call lowercase a. Right, so we've written the same thing down here. And then if we divide through by delta t and take the limit delta t going to 0, we know we can rewrite this as dNA dt, and left over here is UCA times A. So this is the rate of change of moles of A that's entering this space. Now we would like to translate this into a flux. So a flux is a more intrinsic property. And to explain the concept of intrinsic, if you think about our estimate here, you can see that this rate of change of moles is dependent on the area of our system. Right, so our system, our tube, has a specific cross-sectional area which we've called A. Now, the difficulty with this is all our developments will become quite specific to a tube of this size. Now, we would like to get away from that. We would like to work in terms of properties that are independent of the size of the system, because then it's more general and we can make statements that will stay true for longer. So let's instead divide out this influence of A. And so we define a new quantity, capital NA, which we understand to be the flux. And so we are obtaining NA simply by dividing the rate of change of A by the area itself. So dNA dt divided by the cross-sectional area that it's passing through is our estimate of what we call the flux. So the flux tells us the moles per second per area. So it's more intrinsic. It's no longer dependent on the area that our fluid is passing through. It simply tells us the tendency of that fluid to transfer component A. So this flux is a nice general variable, and we can, if we want to find the equivalent rate between this tube and another tube of a different area, we simply do that by taking the same flux and just multiplying by the new area. So this is a nice intrinsic variable, and we can see here if we are going to divide by A, then we just have U times CA here. So the flux, these comments are trying to establish some kind of sense for a flux. So you want to think of a flux as as a kind of almost in the same vein as concentration. So we, in the same way that we have moles per cubic meter, we can think of flux as the molar flow rate per area. So it's how much flow rate have you packed into the area. So molar flux is U times Ca. And this is, of course, on a molar basis. This is the so-called molar flux. We can equivalently estimate the mass flux. So instead of moles per second per meter squared, we can have kilograms per second per meter squared if instead of the concentration, we use the density. So the velocity times the density is the molar flux, the mass flux. Now, taking this concept further, we can, of course, say that the molar flow rate is the molar flux multiplied by the area. That's what we just said. But let's think about this area now. So in the case we've just described, we were discussing the cross-sectional area of this tube. So we had some cross-sectional area here. And now let's say we didn't have a cross-sectional area that was oriented like this. So in this case, we have an area which is normal to our flow. And when we say normal, that means if we imagine the unit normal outward vector from the surface, we can define a vector. So that's how we vectorize surfaces. So if you take any surface, whatever type of surface it might be, you identify a vector which is normal to that surface, and you call that the unit normal outward vector. So in this case, we have an area with a unit normal outward vector which is in the same line as your velocity of your fluid. So the velocity vector of the fluid is incident with the line for the unit normal outward vector. Now let's imagine the case where the area wasn't oriented this way. So drawn here is a tube with an area that has been reoriented somehow. So let's say the area here was lowercase a. So we are just borrowing the notation for the outer tube. Let's say the area was actually a here. And if this area was normally oriented, so if it was drawn like so, then of course you have the maximal flow through this tube. However, if we start orienting this hole differently, so let's say the hole was actually oriented, instead of pointing in the same direction or along the same line at least as the fluid, let's say we had shifted this to 90 degrees. So you can imagine as you change the angle of this hole, then less and less of it is seen by the fluid. So as you shift that hole through increasing angles, right? So let's say we are shifting it by this angle. As you increase the angle of this hole, you will receive less of the fluid that's flowing across that hole. And we can even imagine a situation like this. So let's say the hole was totally blocked off like so. Not blocked off, but let's say the hole was actually in this orientation. Then we can imagine that there's much less flow through this system and there's no direct flow into here. Of course, we know that doesn't really happen due to viscosity and pressure difference. However, just in terms of the direct fluid flow, there's no transfer of fluid across this space, because now your unit normal outward vector is normal to the fluid flow. It's at 90 degrees. It's perpendicular to the fluid flow. And so the way we introduce this concept of angle into our estimates of the molar flux is through the dot product. So first of all, we acknowledge that our molar flux is actually a vector. And so in contrast to the earlier case where we were talking about just one dimension, Now we recognize that velocity is a three-dimensional vector. Then our product of that and the unit normal outward vector is going to be our actual estimate of our molar flux. And from our earlier maths courses, we know that the dot product of two vectors is the product of their magnitudes and the cos of the angle between them. And now we can see here that in the earlier case, let's take this case, your unit normal outward vector is like that, and your velocity is like that. So here the angle is 180 degrees, or pi, and so the cos of pi is -1. So we've got -1 times the area, so we still have a high flow rate. As you increase the angle, and once the angle gets to 90 degrees compared with that, 90 degrees is pi by 2, so pi by 2 is here. So you can see the flow rate through the flux through is 0. So in terms of flux, which is directional, you have a dot product relationship between the velocity and the area. So please do this example. In this example, you've got a gas stream with a given linear velocity and a density and a mean molar mass. And we have a dip tube in the stream, and the area of the hole into the dip tube is 3 square centimeters. And so if we want to achieve some specific molar flux, then what should be the angle that we must use? So we can see that there is already a specific molar flux in the fluid itself, in the bulk of the fluid, and we want to accomplish a specific flux that's through the dipped tube. So if you want to withdraw your component A at a specific flux down into the dipped tube, then there will be a specific angle that we can identify that gives us that flux. And then here, I guess we simply specify some values for that angle, and then we want to know what the molar flow rate through the line will be. Right, so through the dip tube, what's the molar flow rate going to be if we use these angles for the area? Okay, and the solution is here. Here's another example which we'll work through in more detail. So here we have a fluid that's fed by a flow rate Q in. So we have a vessel. Let's sketch it. So we've got some vessel here, and it's fed by a stream with flow rate Q in. And I believe this is simply a given constant, right? So we treat this as some known and constant number. And then we also know the concentration entering in that stream. So there's Ca in here. And then the cross-sectional area is given, and the exit flow is gravity driven. So first of all, there is an exit flow, and it's driven by gravity. So that means this is a liquid phase, and so we've got the height of this liquid is going to drive our flow rate. So there is a certain height here. Let's obviously call that h. And we have an exit flow rate here, Q out. So if Q out is gravity driven, you'll appreciate from your fluid mechanics course that your volumetric flow rate is going to be proportional to the square root of the height. And you can just check your Bernoulli's equations or anything like that to understand that. Right, so your volumetric exit flow rate is proportional to the square root of the height of the liquid in the vessel. And we are asked to develop the material balances and to get the concentration as it's varying. So obviously that's referring to the concentration of component A. So first off, we can say that the height in the system will be the volume of the liquid in that vessel divided by the cross-sectional area. So that's simple geometry. And then we know that the volume of liquid in that tank is changing over time, and that's changing due to the flow in and the flow out. So of course it's increasing with inlet flow and decreasing with exit flow, and the exit stream is gravity driven, so k square root of h, as we said. Then we can write the rate of change of moles of component A in that system. So the rate of change of moles of A is simply the molar flow rate into the system minus the molar flow rate out. And now we have an expression for Q out. And we can rewrite the number of moles of A as the concentration of A in the vessel multiplied with the volume in the vessel. And we know the right-hand side is there. Now, we can see that Ca and V may be changing with time. The concentration of A in the vessel might not have been Ca in initially. So you see, in the system with no reaction occurring, if A is entering, then the amount of A in here will change with the level, but the amount of A with respect to the volume is not changing. So the concentration of A is not changing in here, not as a result of flow or reaction. However, the initial concentration of A in the reactor, which we'll call Ca0, that is not necessarily the same as Ca in. So for example, if you had a concentration of 100, just arb units, let's just say it was 100, whereas the concentration of A in this stream was 1, then you would, in effect, by introducing the stream, you would be diluting component A in that reactor as this level was rising. So the concentration may be changing with time, and clearly the level may be changing as well. So the volume is changing with time. So when we write ddt of CAV, we have to acknowledge that we have to treat this as the product of two time-varying quantities. And so we have to expand this out into V dCA dt plus CA dV dt. Now, dV dt, we have already written and we've identified it as the difference in these volumetric flow rates. So we can simply substitute for dV dt as Q in minus Q out. And then we can retain the right-hand side of the equation. So we just bring that down as on the right-hand side. And we can see here that this term can cancel. So Ca times Q out can cancel with Ca Q out here, leaving us just with Ca Q in and Ca in Q in. So taking the Ca Q in across, we end up with this form. So this is the differential equation that describes how the concentration of A is varying with time in this reactor. And please note here that Ca is the variable of this equation. So that's fine. We know we are solving for Ca as we are integrating this equation. Then Ca in is a constant, so we are treating the inlet concentration of component A as a fixed number. Also the inlet flow rate we are treating as a fixed number. But this V is changing with time. So we can write that maybe more explicitly here like that. And so we need to solve this equation simultaneously with this one, because as we solve this equation, we will get V as a function of t. So we solve those together with these initial conditions, that there's some known initial concentration of component A and some known initial volume in that system. Right, so that's the type of mass balance. And this problem basically just gives us a warm-up. Okay, so that's convection. Now let's start talking about diffusion. So, of course, the bulk movement of fluid that we've talked about in convection is actually a result of many, many molecules moving through. So we've been talking about component A moving through the system, but there might be a large diluent moving with that component A as well. And so now let's first think about a fluid at rest. Let's say in this fluid at rest, we just inject some of component A into that system. So, for example, if the walls here were easy to penetrate and we just pushed a syringe through and we injected a salt solution or something like that, then we would initially have a high concentration of that salt in this region. But as time goes on, due to Brownian motion and due to the electrostatic attraction of the molecules here with the molecules in other spaces, we will have a transfer of that salt across the space. So the molecules will start diffusing away from the original point of entry. So that is the concept of diffusion. And in diffusion, we are claiming that the flux of A is dependent on the difference in concentrations across the space. So here we have a high concentration of A, so Ca at this position, let's call that Ca1, is going to be very different to the concentration here, and call that Ca2, which we can see is 0, right? So there exists a difference in the concentrations here, and if you like, that effectively creates a difference in the electrostatic nature in the fluid. And so we will have, on balance, a transfer of A. So A is in effect attracted to this other region where there isn't so much A around it. So in effect, that's really how we model it. That's how we think of it. So in diffusion, we consider the difference in concentration between two regions, and we specify that the flux of component A, the flux is set up based on the difference in those concentrations. Note here that the fluid is not in motion. We said this is a stagnant fluid, but we are still talking about the flux of component A. So earlier, when we had introduced this notion of the flux, A was very clearly in motion because of the bulk movement of the stream. So there, the flux was all about the velocity. Now we don't have velocity, or velocity is 0, but still A is moving. So we can still talk about a flux of A. So remember, flux is the molar rate of transfer on an area basis. And if you think of it, you can identify a certain rate at which A is moving down this tube. And if you just go ahead and divide by the cross-sectional area of the tube, then that's going to give you a flux of A down the tube. So the concept of a molar flux still exists and is possibly still non-zero, even if your convection flux is 0. So here we are trying to estimate now what this flux might be. And we've said that this diffusion flux is related to the difference in concentration between the two zones. And it also relates to how sharp this difference is. So if the difference persists even in a very short space, so here, for example, you can see a high concentration here, and immediately next to it a very low concentration. Whereas here, to get the same difference, you have to look over a much wider space. Right? To get to as low a concentration, you have to go much further down the tube here. So the delta X is much smaller here compared with here. So if you like, the difference is more concentrated in this region. And we can imagine then that the diffusion flux away from this point is going to be much higher here than compared with here. Here, even as you diffuse away from this higher concentration zone, there's still a component A here which may be perhaps repulsing your effort to diffuse in this direction. So that's going to slow down your transfer rate. So there's a greater space over which the same difference is distributed, and so your diffusion flux is expected to be lower in this case. So we can see that the flux, that the expected flux is going to be proportional to the difference in the concentrations. So the concentration at one value of x minus another value of x, a value at a different x, and we'll call that delta x. And it's going to be inversely proportional to the distance over which that difference exists. So if it's a greater distance, we expect the flux will be lower, right? If it's a short distance, there's a very sharp difference here in concentration, and so we expect a higher flux here. So we can say it's inversely proportional to the distance delta x. Delta x. Now let's also think of, and this we are just saying this is a proportionality at this stage, right? So let's just say it's proportional to. Now also let's think about the sign. We would like, we can see that flux is going to be positive if you have a low concentration here and a high concentration here, right? By flux being positive, we mean there's a tendency for the fluid to be fluxing in this direction. So this happens if you have a low concentration here and a high concentration there. So this is a larger value in x. This is in effect x plus delta x. So we are expecting this number to be low and this value to be high. So if you have a low number here and a high number here, then this is on balance going to be positive, and so this is going to give us a positive number. However, if you look at this, it's x, it's a function of x minus a function at x plus delta x. So this is equal to minus dCA dt. So as we let delta x go to 0, we can see we get minus dCA t dx. So this is minus dCA dx. So your molar flux is proportional to minus dCA dt. And then, of course, to establish some equality here, we have to multiply by some constant, some number which is going to translate from this concentration gradient to a molar flux, and we call that number the diffusivity. So this is what we write, that the molar flux due to diffusivity, due to diffusion, is equal to the gradient of the concentration multiplied with this constant, which we call the diffusivity. So I didn't say it properly first. This is the diffusion flux, and this is the diffusivity. So diffusivity is the constant we multiply by the concentration gradient to give us the molar flux, right? And this is also called the Fick's law of diffusion. So clearly Fick's was the person who did a lot of research in this area, and so that's how we can estimate the flux due to diffusion. Here's another example. We have a 2-compartment cell, and we have different concentrations in the compartments. We have a membrane between the compartments, and it's permeable, so A can diffuse across the membrane. So in a way, this is a fixed distance between those two cells, and the 2 compartments are stirred vigorously. So let's sketch that out. So we have some system, and we have a membrane here, a nice permeable membrane, which is 2 millimeters in width. And then we have a concentration here, Ca1, and another concentration here, Ca2. And then we are also told it's stirred vigorously. So we have a stirrer here, and we have another stirrer here. And the reason we talk about stirring vigorously is because we want to ensure that we don't have a continuous change in concentration here. So if we didn't have the stirrer here, if you have a certain concentration here which is different to the concentration there, then you would get some gradual shift in the concentration between those 2 points. So we don't want that. We want to maintain a sharp concentration difference at the interface, and so we want one concentration throughout the cell. We don't want to deal with the complication, at least not yet, of having a concentration gradient across the space. So let's keep one nice concentration across the whole space here. So I'm just calling that one concentration there, and there's another concentration here. So clearly then you've got the 2 concentrations, and there is a fixed width between those 2 compartments, and hence the diffusion rate between these 2 compartments is going to be governed entirely by the difference between these concentrations. So it's going to be Ca1 minus Ca2 and divided by the distance between those 2, which is 2 millimeters, and I'll just call that a lowercase delta. So we want the diffusivity, so Na, and that's equal to, we know from Fick's law, that's equal to the diffusivity dA. And there's a sign difference here, so we need to say minus. So it depends. If we take x in this direction, right, remember we want minus dCA dt. So dCA dt is actually going to be Ca2 minus Ca1. If we are taking delta as positive in this direction. So that's dCA dt, and then we need a minus sign here. And so we would then substitute our numbers in here. So, well, we don't give numbers in this problem, but let's imagine some situations. So let's say Ca2 was 10 and Ca1 was 5. Right, so we have 10 here and 5 here. Right, if we stick the numbers in, 10 minus 5 is going to be 5, and then divided by 2 millimeters, so that's going to be a positive number. So this is plus 10 divided by plus 2 times 10 to the minus 3, and then times minus something. So on balance, this number is going to be negative. So that tells us the flux is in this direction. And let's check if that's consistent with our understanding. So here we said Ca2 was 10 and Ca1 was 5. So clearly you've got high concentration here and low concentration there. So yes, we do expect flux to be in this direction. Right? So that makes sense. And then clearly you can just stick the numbers in here if you want to estimate Na. Right, so that's how you estimate the diffusion flux if you have all those numbers. And in fact here, this is providing us with the balance if we wanted to know how the concentrations were changing with time. So what we just described here was at a single instant in time. So if at a single instant we knew each of these concentrations, you can estimate the molar flux there. But of course, as time goes on and as A diffuses between these 2 compartments, then the concentrations are changing in each case. So the concentration, if we started with 10 here and 5 here, then over time we expect that what will happen is, here's your 10 and here's your 5. We expect that the concentration will drop in compartment 2, and we expect the concentration will rise in compartment 1, and there will come a point where the concentrations in the 2 compartments are approximately the same. So we can write a material balance in terms of the rate of change of component A in each compartment, and that's exactly what's done here. Note in this case that we do treat the volumes in each case as constant, and in fact what we ought to be doing is rewriting here. We should say this is V1 and this is V2, right? So we can integrate these two equations together and we can estimate the changes in those concentrations. If you solve it in Python, you can read the code here. You can see that's what's happening. So I've used different initial concentrations here. You can change this to 10 and 5 if you like, and you can see how the concentrations eventually stabilize here. Okay, so much for diffusion on its own. Now let's talk about the interaction between diffusion and convection. So let's say our bulk fluid was in motion and we knew that diffusion was also significant in our space. Right, now we are going to establish the basic terminology. So if you take J sub C as your convection flux and J sub D as your diffusion flux, then you can identify the two fluxes like this. That's fine. Well, I guess that's just definition so far. So, and then now let's talk about a multi-component mixture. So let's say you had your component A, but there was another component in that system as well. And so A was diffusing against some other component. Right, so number one, we can introduce the basic definitions. We can say there does exist a certain total concentration. And you can simply add them if they are on the same basis of volume. So of course, if they are different phases, you can't add them. If it's a gas and it's got one volume and you've got a liquid with another volume, then you can't add them. But if you are talking about species in the same phase, then they are occupying the same volume. So the basis of concentration is the same, then you can just add them together. For a gas, you can also estimate the concentration using your equation of state. So if it's an ideal gas system, so if your pressure is low enough, then this relationship holds. So you can estimate concentration simply as P over RT. And then you can go on to define your mole fractions. So if it's liquid, the standard is to use an X for liquids. So the ratio of the concentration of component I to the total concentration. And for the gas, the same thing. For the gas, you can also rewrite the concentrations in terms of the partial pressures. So P sub I is the partial pressure of component I divided by RT. So that's the concentration of component I. And then the total concentration P over RT. And of course, RT can cancel, so leaving you with the ratio of the partial pressures. Obviously, all these fractions add up to ones. You can also define your mass fraction like this. So if you take a basis of 1 mole, then Xi is the number of moles of component I, so number of moles times the molar mass. That's the mass of component I. And then if we do the same thing for all components, we get the total number, the total amount of mass in that 1 molar basis. And so this fraction is the mass fraction of component I. So if you want the mass fraction of I, then you multiply the mole fractions by the molar masses and divide by the total amount. If you wanted the mole fraction and you were given the mass fraction, right? So in this case, we were given mole fractions and we wanted mass fraction. If we had the reverse, if we wanted mole fractions from mass fractions, then again, you just take the mass fraction. So in this case, you take a 1 kg basis. So all components add up to 1 kg. So the mass of component I is omega I. And then if you divide mass by molar mass, you get number of moles. So that's the moles of component I, and divided by the total number of moles, that gives you the molar fraction. Okay, so in a way, these are just reminders. I expect that you do know all these things anyway. Right now, a bit more useful, we can also define the molar average velocity. So we can say in our flowing fluid that there exists a certain velocity, and we could base that velocity on the number of moles that are flowing around. So we can say there exists some average velocity in terms of moles. So if you take that and multiply by the total concentration, right? So what's written here is very much just the total movement of our moles, and then we should get the same answer if we took each component, and if we took the velocity of each component and multiplied by the concentration of each component. So and in fact, the only thing we are doing here is defining an average molar velocity. So the average molar velocity we get just by taking this thing and dividing by the total concentration, like so. And we can do the same thing for the mass, right? So you can say the mass average velocity multiplied by the total density equals, and then if you multiply the individual mass velocities by the individual densities, then you'll get the averaged mass velocity. And these two things might be different, right? The molar average and the mass average, they might be different. Right, so that's just preparing some quantities for what we are doing now, which is more significant. So now we are interested in multi-component mixtures. So let's first just talk about a binary mixture. So we've got components A and B. And now we are talking about component A diffusing through component B. And again, we can define our diffusion flux. And here we are being specific in the axial direction, right, in some dimension z. So this is the diffusion in the z direction of component A. And according to what we defined before, it's minus dAB, dCA, dZ. Okay, so that's fine. Now let's define an average molar velocity uz, right? So just note this is the molar velocity, right? And this is the average. So I'm not going to use as much notation as here. I'm not going to write mole average. So we'll just call uz the molar average velocity. We will also call the velocity of component A to be UA. We'll define the velocity specifically of component A. And A's velocity might be different to B's velocity because A might be diffusing faster than B, or the reverse, and things like that. Right? So we can say that if we compare the velocity of component A to the bulk velocity. Remember, uz is the average molar velocity, so it's the average velocity of all the species together, including A, but other things as well. So if we take component A and subtract off the bulk movement, right, and remember Ca times the bulk movement, that's your convection. Now you are saying component A might be moving faster or slower than the bulk movement. So this difference must only be due to diffusion, right? So let's just maybe try and sketch something about that. So let's say you have in your pipeline, you've got your bulk fluid flowing along. So you've got your species moving at the bulk velocity, U, and I'm just going to call that U over bar for emphasis. And then you observe within that there's a component A here, and that seems to be moving even faster than the bulk fluid. Now the only way that's possible is if there's something other than convection that's driving A. Right, so A is being carried along with the bulk fluid, but on top of that, it's moving even faster. So the only remaining source of momentum for A is diffusion. So we can say here the difference between A's velocity and the bulk velocity must be due to diffusion. So JAZ, the diffusion flux, must equal this difference, which is in effect also a difference of fluxes, right? And so here we just rearrange this a little bit, and so UAZ, if that stays there, and if we take this term across here, then that's CAZ minus DAB dCA dZ, right? So your average molar velocity we had simply established here as the sum of the species divided by the total concentration. So here we are just expanding that out. We are multiplying CI/UI, the sum of that divided by the total concentration C. So we are substituting that in here in this factor. And then you've got CA times that. So it's going to be CA over C. So CA over C is, of course, the mole fraction XA. Right, so we could rewrite this whole thing CAUZ as XA times this thing. Right, so that's how we get that relationship. And now we can substitute this for this term. Right, so coming back to what we were doing here, where we were counting up fluxes, we've been trying to get rid of this this form, right? Because it's got this unpleasant UZ. We don't know how to estimate this bulk flux. We want to work in terms of the individual velocities here. So now we've substituted from our earlier definition, and we've gotten rid of this UZ. Now it's all in terms of the individual velocities. So now we just by substituting that, we can say the total flux of A we know is equal to the concentration times the velocity of that A, and we have found that that is equal to that plus that, and we found CAUZ is equal to all this, so we substitute here, and then the remaining piece, which is here, noting that we've multiplied by total constant, or we've rewritten, instead of dCA dZ, we've written dXA dZ, and we've taken out the C here. So that's C times that. Okay, so that's how we can estimate the molar flux. And note that this is not trivial, right? You might automatically want to write here CA times UZ. And you see, you have to be more careful than that. It's this term is significant in comparison with our intuitive way of writing the convection term. The diffusion term is fairly intuitive, but this part is not really intuitive. So you have to be somewhat careful here. And so that's your molar flux of A. And then this is all written specifically in dimension Z. We want more generally a flow in 3 dimensions. So instead of just in one direction Z, we'll go back to the vectorized form. So we can rewrite molar flux of A as a vector, and we can rewrite UA as a vector. So that's our flux there. And then we can expand on this side also. So we can say that's equal to, and then here x is of course a scalar, but now z we are considering all directions. So instead of ddx, ddy, ddz, so I'm just going to explain here this operator del. The Dell operator is this vector ddx, ddy, ddz, and I should say transposed. So if you write del dot xa, so, and that's the Greek symbol nabla, so del dot xa, then you are in effect multiplying, you are in effect taking the derivative with respect to xa in each dimension. What's a little bit confusing here, or there's a slight notation collision using x here and x there. This x means mole fraction, and this x, of course, refers to the spatial dimension x. So just take note of that. So if xa is a scalar, then this is xa then this is a vector of derivatives. Right, which is fine because we have a vector here as well. Or yeah, this is a vector, so we do expect a vector output. So this is going to be a vector. These are all vectors. Sum of a vector is a vector times a scalar, that's a vector. So this is all a vector. Right, so that's the balance that we get. So that's your molar flux of component A. So here's another nice example. You've got a system with a pipeline. So you are given the diameter and the length, and the molar flux is known, and we want to maintain a specific concentration at the entry point and another concentration at the exit point, and the profile is linear. The diffusivity is also known. So we are losing component A from the tube. So there's some diffusion out of the tube, across the walls of the tube, right? So we've got some diffusion in this direction. So we've got diffusion out of the tube. We've got one concentration here, we've got another concentration there, and we have a flow rate. Well, we are given as a flux. Right, so we want to know what's the molar loss rate from the tube, what's the velocity.